Hey everyone. In this video I'm going to talk about probability and conditional probability. So as I mentioned in the previous video, we use probability as a measure of uncertainty. And ultimately probability, or a lot of probability theorems, are based on a set of three simple axioms that I'm going to talk about in a second. And from these very simple axioms, basically a countless number of useful theorems, like the Bayes theorem that I mentioned, can ultimately be derived, right? And so in this section, we focus on this kind of conceptual understanding and talk about how we can define, interpret, and compute probabilities. Right? So let's jump right in. What is probability? As I mentioned, probability is a mathematical model of uncertainty or chance with, in practice, ultimately two alternative interpretations. Right? And on the one hand, we have the frequentist interpretation of probability, which basically interprets probability as a result of repeated experiments, where the probability ultimately represents the limit of the relative frequency with which an event of interest occurs when the number of experiments repeatedly conducted under the same conditions approaches infinity, right? So, for example, if we have, if we flip a coin, we could, we could flip it once and we could record is it heads or tail. We could flip it 100 times and then compute the proportion of heads versus tails, and that ultimately, if we increase the number of times we flip that coin to infinity, the relative proportion of heads versus tails is then the frequentist probability of observing heads versus tails, right? And intuitively, of course, that makes a lot of sense, but there are some difficulties because this frequentist interpretation kind of implicitly or implies that we have some repeatable event, right? And we approximate kind of a relative frequency in repeatable events, right? But what about events where this kind of idea of repeating the experiment doesn't quite work, right? So we talked about prior to the election, we talked about forecasts for the election result, right? So what does it mean that the probability of Trump or Biden winning the election prior, to November 3rd was, about 90%, right? It's not like we can rerun the election, 1,000 times or 1,000,000 times and then approximate this relative frequency of, Biden winning and use that as a probability, right? So with these one-time events, it's kind of difficult to think about probability from a frequentist perspective. Other examples could be, what is, if you look at the weather forecast and you see the chance of rain tomorrow is 80% or something like that, right? So how do we think about these probabilities in the context of repeatable events? It's not like we can repeat tomorrow multiple times and then look at the relative frequency of rain happening versus not, right? Of course, there are ways around that. We can kind of think about, kind of like parallel universes and kind of have like a thought experiment of potential repeatable events or repetitions of these one-time events. But of course, that requires a little bit more additional kind of steps, right? So in contrast to this frequentist interpretation, which is grounded in this idea of repeatable events and approximating the relative frequency with which an event occurs, is the Bayesian interpretation of probability. In the Bayesian kind of framework, probability doesn't represent this relative frequency, but rather represents the subjective belief and is basically a personal measure of uncertainty, right? And so it kind of it lends itself more easily to, for example, interpreting probabilities in these one-time events, like, what's the probability that Biden wins the election prior to, of course, as a forecast, right? So here, probability is a measure of one's subjective belief about the likelihood of an event occurring, right? And that's an important distinction. And you see in the literature and in political science, you see debates between kind of frequentist and Bayesian applications and interpretations of certain of probabilities, right? The important piece to keep in mind is that these disagreements are ultimately only about the interpretation of what these probabilities ultimately mean, right? The mathematical properties of probability are ultimately driven by the same three axioms. Whether or not you call yourself a frequentist or a Bayesian in terms of how you interpret probabilities, the underlying axioms are the same. The mathematical properties of probability are ultimately the same, right? So this is more about interpretation than it is about the underlying math, at least when it comes to the probabilities themselves. Of course, Bayesian statistics and frequentist statistics also have differences in terms of methods, but we'll get to those later throughout the next semester in 702. Okay, so after kind of covering those kind of broad interpretations of probability, let's get to these. Let's first talk about some few key concepts, and then we'll move on to these three axioms that I now mentioned a couple of times, right? So before we get to that, we have to cover a few kind of key concepts so we know what we're talking about. I mentioned the idea of an experiment, right? And the experiment here is different from the experiment that we talked about when we talked about causal inference and randomized controlled trials. When we talk about experiments and probability, all we mean is that this is an action or a set of actions that produces stochastic events of interest, right? So flipping a coin or rolling a die or voting in an election is an experiment in kind of this, in the context of probability theory, right? It's something, an action that has a stochastic component that creates some outcome, and we're interested in the probabilities of these outcomes occurring versus not, right? The sample space, which is often denoted with this omega, denotes all possible outcomes of the experiments, right? So when we talk about flipping a coin, that would be either head or tail. When talking about rolling a die, there would be any number between 1 and 6 if you have a regular 6-sided die. Or when we talk about voting in the last election, we could think of 3 possible outcomes as abstaining, voting for Biden, or voting for Trump. We could even expand this to third-party candidates, but for now, let's keep it with the Democrats and Republicans. And then we have an event. What an event describes is any subset of outcomes in the sample space, right? So for flipping a coin, an example could be I flip the coin and I get a head rather than a tails, right? But this could also not be. It doesn't have to be a single element of the sample space. It could also be a collection of elements in the sample space, right? So for example, rolling a die, an event related to rolling a die could be we're rolling an even number, so 2, 4, and 6 rather than 1, 3, and 5. It could also be kind of the complements of certain events. So for example, an event could be do not abstain, right? So any other outcome but abstaining could be an outcome in the when we think about the experiment of voting in an election. Okay, so having this basic framework of an experiment, the sample space related to that experiment, and a specific event as the realization of the sample space or of one of the or a subset of the outcomes in the sample space, we can then denote the probability as P of A. As the probability that an event A occurs, right? So A is this kind of the placeholder for a specific event, and P of A is then the probability that that event would occur. And in general, one basic kind of rule in probability theory is that if all outcomes are equally likely to occur, what we then have is we can basically count the number of elements in A and divide that by all the number of elements in omega in the sample space to describe the probability of A occurring, right? So this is straightforward, for example, in the context of rolling a die, and the event would be getting an even number versus an odd number, and that would be three elements in the sample space for which that belong to the event A, which is, as I said, 2, 4, and 6. And the total number of elements in omega is, of course, 6. And so the probability of rolling an even number would be 0.5 or 1/2. Okay. All right. So now, after we talked about these basic concepts or these key components to describe probabilities and probability events, now let's move to these 3 axioms. Right. So the first axiom is that the probability of any event is non-negative, and this is simply stating that P of A for any event A is larger or equal to 0. So there are no negative probabilities. Straightforward enough. Second axiom is the probability that one of the outcomes in the sample space occurs is 1. So that means basically that all the elements, the probability of anything happening or all the things happening, or I should say any of the things happening in the sample space is equal to 1, right? So the upper bound of the probability of probabilities is basically 1. So the first 2 axioms together basically imply that probability ranges from 0 to 1, right? So all outcomes in the sample space all together, any of them happening, the probability of any of them happening is equal to 1. That's also straightforward, okay? And the third axiom is the addition rule. If events A and B are mutually exclusive, then the probability of A, and this is now using set operations, the probability of A or B happening, so the probability of A union B is equal to the probability of A plus the probability of B. Okay, so this little cup symbol indicates for 2 sets the union of those 2 sets, or in other words, it's the probability of A or B happening. Okay, and if both are mutually exclusive, then that is just the sum of the 2 probabilities. Okay, and these axioms of probability, or these probability axioms, are pretty straightforward and incredibly intuitive and make sense. But the fascinating aspect is that from these 3 axioms, basically the entire probability theory can be built, right? So all we need is these 3 axioms, and all these later rules or theorems, like the Bayes rule or Bayes theorem, law of total probability, all these things that we kind of talk about later on can be derived based on just these 3 axioms, whether you're interpreting these as Bayesian probabilities or frequentist probabilities. Okay. There are a couple of useful rules of probability that wait a second. There are a couple of useful rules of probability that I want to talk about briefly that we can again derive from these axioms, right? The first one that is important to keep in mind in many cases when you have a problem where you're trying to compute a certain probability or an unknown probability is that sometimes it's easier to compute or calculate the probability of the 1 minus the complement of an event occurring rather than the probability of the event itself occurring, right? So for example, if we are interested in the probability of voting or someone voting in an election rather than abstaining, and we know that this probability is 0.6, we know that the probability of the complement event, so the probability of not voting essentially, is equal to 0.4. Okay. The second useful rule that we're going to refer to later on is the law of total probability, and that's the that rule indicates that the probability of A occurring can be kind of you could think of it as basically dividing the probability of A as 2 subsets. One is the probability of A intersect B, so the probability of A and B happening, plus the probability of A and the complement of B happening. So this C always indicates the complement or not, or the opposite of that event happening, right? So in other words, the probability of A happening is equal to the sum of two separate probabilities. One, the probability of A intersect B, and the probability of A intersect complement B. So that's the probability of A and B happening at the same time, and that's the probability of A and not B happening at the same time, right? The third rule is the general addition rule, which looks at the probability of the union of two events. So that means the probability of A or B happening, and that's equal to the probability of A plus B minus the probability of A intersect B, right? And we're going to look at this in a visualization that kind of makes this more clear, right? And this is kind of, if we go back to this addition rule, we said that if two events A and B are mutually exclusive, then the probability of the union of those two events is just the sum of those two probabilities. But more generally, if two events are not mutually exclusive, what does that mean? That means that that there is a non-zero probability that A and B happen together, so both happen at the same time. So that's the probability of A intersect B. The probability of A and B happening at the same time has to be subtracted from the probability of A, from the sum of the probability of A and B, right? So to kind of visualize this or illustrate this visually, we can always kind of think of these probabilities and sets in terms of Venn diagrams, right? So we have two events, A and B, and now these two events are not mutually exclusive, right? So there is a certain intersection between those two sets of events where both A and B are happening, right? And these are everything outside here is kind of the remaining sampling space, right? So the general addition rule, now kind of visualized, means if we want to compute the probability of A or B happening, so A union B, that's equal to the probability of A happening, of course, plus the probability of B happening. But as you can see, if we just look at the probabilities of those individual events and just sum them up, what we kind of count twice is this intersection between A and B. And that's why we have to subtract P, the probability of A intersect B. So we have to subtract the probability of A and B happening at the same time, because otherwise we would count it twice, kind of in this, visually in this Venn diagram, when we take into account the probability of A individually and the probability of B individually, right? We can extend this essentially to more, oops, I'm not moving myself in the right direction. We can extend this to more than two events essentially. So for example, if we, and this is kind of more generally the inclusion-exclusion principle, where if we look, for example, at the probability of A union B union C, so the kind of any of the events A, B, or C happening, the same logic applies, and you can kind of you can pause the video and kind of go through each of those steps. We first add the three probabilities together, probability of A plus probability of B plus probability of C, and then kind of similar to the two event scenario, we're subtracting these intersections between A and B, the intersection between A and C, and the intersection between C and B. These are the subtractions here, probability of A intersect B, B intersect C, and A intersect C. But then we kind of subtracted this intersection of all three events to one time too many, essentially. And that means we have to add the probability of A intersect B intersect C, so that's the event in here, in order to kind of get the accurate probability of A union B union C, so any of those events happening, okay? So when we think about probabilities in terms of sets of events, one thing that becomes very important is to count the number of possible combinations, and that's where permutations and combinations comes in, right? When we talk about permutations, what we mean is we want to count the number of ways to arrange objects, right? So for example, if we have 3 letters, A, B, and C, and we can kind of arrange them in different orders, we have 6 different permutations. So ABC, ACB, and so on, right? We can also think about this, if we kind of want to count how many permutations we have, we can think about this as a process of sampling without replacement, right? So the number of permutations of n elements taking k at a time, or we have here 3 elements and we take 1 at a time and kind of record the ordering. And we can generally, if we want to kind of count the number of possible permutations that we can take, that is denoted as n permute k, and that is equal to n factorial divided by n minus k factorial, where of course the factorial, the sign for the factorial indicates that if we're, for example, 5 factorial, that's equivalent of saying 5 times 4 times 3 times 2 times 1. And so the general kind of formula to count permutations, if we have n elements and take k at a time, the formula is n factorial divided by n minus k factorial. Right? Combinations, on the other hand, indicate ways to select objects without regarding, just a second, ways to select objects without regard to their arrangement, okay? So, for example, we have the number of combinations of k distinct elements from a pool of n elements, and we're going to look at an example in a second. The notation here is n choose k, or what we more often see is this notation, n choose k, which is equal to the number of permutations, n permute k, divided by k factorial. Okay, so this, if you plug this in, you get n factorial divided by k factorial times n minus k factorial. Okay, so those are basic rules, and we're going to look at an example in a second. Just a second. Oops. All right. I think I'm going to take a break here and go through 2 quick examples of permutations and combinations in the next video.